In the last module, I gave you an introduction to general ventilation, indoor air quality. We talked about some types of contaminants or conditions controlled with general ventilation. We looked at some sources, potential sources of indoor air quality problems. And then we talked about sick building syndrome and building-related illness. Again, sick building syndrome, building-related illness are similar, but there's one major difference. With sick building syndrome, you're not able to identify a specific cause of the problem. With building-related illness, you are able to identify a specific cause of the problem, whether it's VOCs from the paint or inadequate ventilation system or some other problem with the ventilation system. But anyhow, let's go ahead and continue our discussion. We will finish up this unit with this module. Let's talk about some triggering events. Again, events that may cause poor indoor air quality. Again, we kind of talked about this already when we talked about sources of indoor air quality problems, but this is a little bit more specific. This is focusing perhaps on some of the more common triggering events that can result in indoor air quality problems. Yeah, we're talking about a situation maybe where the air inside the building is fine, but something happens, and after that event occurs, we start noticing problems with indoor air quality. One change or one triggering event could be simply an increase in the number of workers in a workspace. And it is possible to put too many workers in a space and there's not enough oxygen available for that number of workers. And that's the kind of situation we're talking about here. Also, increased number of workers in the space, it may result in odor problems. It may result in problems with communicable disease transmission. I mean, you can overcrowd a space and there can be real health concerns resulting from that overcrowding of a workspace. It could be a remodeling job, a renovation of a workspace, or maybe it's new construction. But when you go in and remodel or renovate, you're disturbing dust and other potential contaminants that may have been laying dormant for many years. But you just go in and stir up the atmosphere. And with new construction, I mean, a good construction company, a good general contractor is going to thoroughly clean up the building and get it ready for occupation. And it's also up to the building owner. Whoever hires a construction company should have that in the contract, that this building will be suitable for occupation at the end of the project. Meaning it will be cleaned up, dusted, air cleaned, and so on and so forth. But this can be a problem leading to indoor air quality. And it could be even maybe you've got a new heating, ventilation, air conditioning system, or maybe there's been a new air handler installed in the HVAC system, or maybe a new run of ductwork has been installed in the HVAC system. And any changes to the HVAC system may result in indoor air quality problems because maybe the air is not moving as efficiently as it needs to with the changes that have occurred. It could be new furniture or equipment in a space. Again, new carpet, new copier, a new paint job. New paint may be all it takes to have some problems with indoor air quality. And now most of the time with a new paint job or new carpet, it's going to be temporary. But there are cases where it's gone for an extended period of time and health or illnesses have resulted from just something as simple as new carpet or new wood flooring or new paint in a workspace. It could be a new work operation. Maybe there's some type of task that's being performed in a work area that had not been performed in that work area before. An example would be a machine shop. In a machine shop environment, you're normally not going to have a lot of welding going on. But let's say the machine shop environment adds welding operations into the same environment where you're milling metal parts, or where you're doing other operations with metal. That welding, that new operation, can create contaminations. And in the case of welding, we're talking about the potential for dangerous contaminants with the zincs and the chromiums and the other contaminants that are generated during welding. Maybe it's not a new work operation. Maybe it's just an increase in the rate of production. If the machines are working longer and they're working harder, they may be producing more emissions. With the increased rate of production, you're starting to see indoor air quality problems that you did not have before the rate of production increased. Or it could even be a seasonal change. We have allergy seasons in Oklahoma, and most other states will have their allergy seasons as well. In Oklahoma, it seems to be the fall of the year and the spring of the year are the allergy seasons. And there could be indoor air quality problems associated with that seasonal change. Again, and that's something that we could, I don't want to say might, we would be able to implement some changes to mitigate seasonal change allergen type of problems. It may be a different filtration system. It may be just changing the filters in the system. And that's one of the biggest problems you see with HVAC systems and general ventilation systems. If they have an air filtering element, it's got to be maintained properly. You got to change the filters. You got to clean the filters. Whatever type of maintenance is required, that's a big part of maintaining the functioning of a system. If you never change the filters, you let the filters get clogged up, that's going to affect how well your system is moving air. And it could also shorten the lifespan, the usable life of that ventilation equipment. Okay, these are some triggering events that could end up with some complaints from workers, some illnesses from workers. And I'm talk about this under the heading of some qualitative indicators that may suggest we have a poor air quality problem. One of these indicators, as a safety manager, pay attention to this, and they may come to you with complaints. They could be saying it's too cold, it's too humid, the air feels stale, I can't breathe, I developed a rash, something like that, or the odors are bad. But with some of these complaints, we might be getting into the area of what I would view as another indicator of potentially poor air quality. Illnesses or medical conditions. Symptoms of sick building syndrome or building-related illness. Breathing problems, headache, a rash, maybe blood pressure problems, loss of appetite, nausea. And as a safety manager, if we encounter any of these types of complaints from our workers, that might be an indicator that we need to take the next step and do an indoor air quality investigation. Another possible indicator, absenteeism. Could be related to the medical condition problem. Could just be, hey, I don't feel right when I'm at work, so I'm just going to stay home today. But increased absenteeism could also be an indicator of potential air quality problems. Lowered productivity. If the air's not right, the temperature's not right, if there are allergens floating around in the air, that's going to affect people's production. And this kind of goes along with comfort to some degree, but comfort, indoor air quality is important for production. And there can be illnesses result if it's not managed. But again, as a safety manager, if we're hearing any of these complaints or noticing any of these indicators, we may need to conduct an indoor air quality investigation. Now, your textbook has a lot of lists and tables and so on and so forth that can be used, that are useful. I'm not going to go into all the different lists and checklists that your textbook goes into. I'm just going to outline, 4 basic steps, and then a fifth step that we may need to execute in some cases. But first of all, the first step in an indoor air quality investigation would be to talk to your workers. What are their complaints? What's going on? Do they feel any symptoms? Are they having headaches? Have they developed a rash? Do they feel nausea or sick at their stomach? Also, as part of this interview with your workers, you want to try to identify parts of the building that may be having more problems, complaints, or symptoms than other parts. If you can identify one wing of the building or one floor or one set of offices that seems to be the concentration for your problems and your complaints, your symptoms, that's going to help you come up with a solution. It could be that the ductwork supplying those offices or that section, there's a problem with that ductwork. Maybe it's not moving enough air. Maybe there are contaminants in that run of ductwork. So interview your workers, try to identify parts of the building where the symptoms, the complaints seem to be concentrated. You would also want to do some type of sampling. You want to take some air samples. Grab sampling is a real common method for IAQ investigations. They go in and take a cross section of the air in an area. Either use the grab sampling canisters that we talked about previously, or they use the Tedlar bags that we talked about previously. And what you would want to do is take multiple samples from around the area. Don't just take one sample. Well, I guess if it's a small area like one office, one sample would probably be sufficient. But if it's a larger area, like a whole group of offices, take a sample from each of the offices. If it's a floor of a building, take samples from different areas on that floor. Also, take some measurements with your direct reading instruments. The simple personal monitoring devices can give us useful information. Most of the time, it's going to be the oxygen levels that's going to be the most useful. But with these direct reading instruments, you would be able to identify problems with the oxygen level. And other direct reading instruments can also be purchased or set up to test for other contaminants as well. But your standard off-the-shelf personal monitoring devices, they're going to test for H2S, which is probably not a problem inside of a building. Could be, but probably not. It's going to test for the lower explosive limit. Normally, it's calibrated to methane gas. Probably not a problem inside a building, but could be. And it's going to also test for carbon monoxide, which, again, that may be a little more, it's probably good to take CO readings, carbon monoxide readings also, because that could be a problem. Maybe something's not vented properly. If it's a gas-fired furnace in a building and it's not vented properly, there could be carbon monoxide that's being spewed throughout the ductwork. That's a potential problem. Then the fourth gas most commonly tested with a personal monitoring device would be your oxygen level, and that would certainly be of interest also. But you've taken some samples, you've done some monitoring with direct reading instruments. You also want to do a thorough investigation of the ventilation system. You want to look at static pressure, velocity, the air volume being moved by the system, the rate of room change. Also, look at the physical structure of the system, the location of supply registers, the location of return ducts, return inlets. Those types of structural issues should be examined also. After you've gone through these 4 steps, if you still aren't able to identify and correct the problem, maybe you need to bring in a specialist, a consultant. And don't be too proud to ask for help. Bring in an indoor air specialist to take some additional readings, to look more specifically at certain components of the ventilation system. But again, if you have indoor air quality problems, headaches, nausea, complaints from workers, we need to stay on the mystery until the mystery's solved and the problem's corrected. Yeah, as we said previously in the previous module, a lot of indoor air quality problems are simply not having good ventilation through the system, not getting a good supply of fresh air into the workspaces. And what I want to look at now are the fresh air supply recommendations. And these are common recommendations. They're part of building codes. Several different agencies promote these recommendations for the amount of fresh air needed in workspaces. Now, at the very minimum, we need to bring in 5 cubic feet per minute per person of outside air. 5 cubic feet per minute of outside air per person. That's the absolute minimum. And a lot of experts argue that that's really not even close to being adequate. But that is a minimum standard that goes all the way back to the 1900s. If it's an office environment, or you could apply this to classrooms and a lot of different work environments, not just offices. And this is a better recommendation, I think, than the 5 CFM. But this recommendation is 15 cubic feet per minute per person in workspaces. If there's an area where tobacco smoke is being generated, the recommendation is 20 cubic feet per minute per person. And if it's a smoking area, a designated smoking area, 60 cubic feet per minute should be supplied to those spaces. When designing a general ventilation system, these recommendations should be applied. You should design a system to, in my opinion, provide at least 15 cubic feet per minute per person. If you've got an area where there's going to be 30 people in a classroom, for example, let's have 30 times 15. What would that be? 450 cubic feet per minute for supplying air in that space. Again, and it all starts during the design phase. But let's say we're working in a building where the system's already in place. Then we need to do our investigation, identify the volumetric airflow into the space, and if it's not good enough, if it doesn't meet these recommendations, then we need to think about making changes to the system. Again, this fresh air can eliminate many indoor air quality problems. Now, the picture to the right, I just threw that in there for fun. That harkens back to a day when it seemed like every adult smoked. And a lot of little kids might have smoked too. Children would start smoking fairly early, back when smoking was considered acceptable. And if we go back into certain periods, there are cases where doctors prescribed smoking to some of their patients. Certainly, it's not that way now, thank goodness. There's a lot of toxins in smoke. Some numbers, just for comparison purposes. 40% of Americans smoked in 1965. And again, I'm going to assume, this is from the Scientific American, I assume they're talking about 40% of adults smoked in 1965. In 2012, only 18%. But one thing that we have going on right now that may be the new smoking is vaping, the e-cigarette. And some research they're starting to do some research on e-cigarette smoke and the toxins that are contained in e-cigarette smoke or vapor. And there are many of the same toxins in an e-cigarette vapor that you would find in tobacco smoke. So it may be the new smoking. There's also studies suggesting that e-cigarettes are a gateway to smoking conventional cigarettes. We still have it still remains to be seen the impact that vaping is going to have in our country, around the world. It's becoming more and more popular. But again, as the research starts to come out, we're starting to see some regulations being implemented and some other measures being taken to try to mitigate the problems associated with e-cigarettes and vaping. I'm hoping it's just a fad that will go away, but who knows? It remains to be seen. We try to predict the future. A lot of times we just get ourselves in trouble, so I'm not going to try to predict the future. Talk about what could be a problem, however. All right, workplace temperature is important. We can use our general ventilation systems to control workplace temperature. And I'm going to kind of speed up through these points. A lot of these points we've already talked about. But research has suggested that the optimal temperature for productivity is around 71, 72 degrees Fahrenheit. And here's one of the studies summarized that came to that conclusion. It found that at 71.6 degrees, you would see your highest productivity. And there are other studies like this as well that set this optimal range, 71, 72 degrees. But temperature, if it's not managed properly, can become a serious safety issue. If people are sweating, distracted, they're so hot they can't concentrate, that can affect productivity and safety. There are direct illnesses associated with high temperatures and low temperatures. Heat-related illnesses, cold-related illnesses. So it's important to manage our temperatures. Depending on what kind of workplace it is, proper temperatures are required to manage the materials being used. Temperature that's not managed properly could also cause damage to other materials, not just spoilage, but other types of damage as well. And a lot of this also applies to humidity. 30 to 60% humidity is the desired range. I haven't seen anything in the research identifying an optimal range for productivity, but what you'll see in a lot of the codes and standards is 30 to 60%. That's what we should be shooting for with our humidity levels indoors. If we keep our humidity levels where they need to be, that's going to help control fungus, bacteria, virus, allergens perhaps, black mold, Legionnaire's disease, or diseases like Legionnaire's disease where bacteria or viruses develop in a humid, moist environment. And also, proper humidity can contribute to productivity, and it can also prevent spoilage or contamination of materials. Workplace nuisance odors. Again, we don't want to overlook this. You might have a flatulent person that's just distracting everybody and becoming a safety hazard. You don't want that. Again, it's really more about comfort of workers, but comfortable workers are more productive. Comfortable workers are not distracted, and they're going to be safer workers. And there could also be spoilage or contamination issues. Let's say if it's a clothing store that has an odor problem, and the odors contaminate the clothing, that's going to hurt the bottom line for that store. They're not going to be able to sell a pair of jeans or a shirt that smells bad if you have odor problems within your retail space. Or it could be a warehouse also. It wouldn't have to be the retail space. But there can be odor contamination of materials. And we've talked about workplace oxygen levels. Too many people consuming oxygen in a space can result in low oxygen levels. Of course, our optimal is 20.9% or 21%. And there's a little bit of range there, like 19.5% to say 22%. But once you get below 19.5%, you can start seeing some physical effects. People are not able to concentrate. You get down into the really low ranges. If you get, it can be fatal at a particular point. Got to have oxygen to survive. Now, optimal oxygen levels, if their ventilation system is working properly, it can be achieved without a lot of additional effort. Now, there are ventilation systems that are designed to bring in fresh air from outside sources based upon what sensors are telling the system about the O2 level or the CO2 level. If O2 drops below a predetermined level, or if CO2 increases above a predetermined level, that will cause the system to switch on and bring in more fresh air. And what we're talking about here is what's referred to as demand control ventilation, where the system is switching on and off based upon occupant loading or the number of people in the area. And there are various types of systems or sensors that are involved or can be used to control a demand control ventilation system. It could be some type of counter, like a turnstile. People walk through the turnstile, and every time somebody walks through the turnstile, the count increases by 1. And as count increases, the system is programmed to work harder, provide more air. There are also automated video systems where you're using video and computer programs that are counting people as they enter and exit a space. And it starts with a video surveillance, and then the system is set up to observe the video, count who's coming, who's going, and then that will make adjustments to the airflow into the space. Could be oxygen sensors. If there's oxygen that drops below a certain level, the system blows, brings in more air. Carbon dioxide is too high. If there's too much carbon dioxide, the system supplies air to the space. Could also be based upon temperature or humidity in an area. More people enter a space causes the temperature to increase. That sends a signal to the system to provide more ventilation air. And just to summarize, when we're talking about demand control ventilation, we're talking about a system that's programmed to increase airflow when more people are in the space. And a variety of sensors that we've talked about may be used in this type of system. Another concern, and something, we're all getting a good lesson in infectious organisms and allergens with what's going on with coronavirus. This is another concern that we can address with our ventilation system. We can provide filtration designed to capture microorganisms. One type of filter is the electrostatic filter, and there's a picture of a passive electrostatic filter, which uses a negative charge to capture positively charged particles. Then you have your HEPA filters that we've talked a lot about that can capture 99.97% of particles 0.3 micron and larger. And 0.3 micron is really small. But one thing that has to be considered, a lot of microorganisms are smaller than 0.3 micron. And we'll look at a chart here on the next slide that shows the sizes of different types of microorganisms and particles and other potential contaminants. Another thing about HEPA filters, you have to make sure that the system is designed to operate with a HEPA filter because they can restrict airflow and cause problems in your ventilation system. So you need to make sure the system can handle a HEPA filter. Your home air conditioning system, you probably wouldn't want to just go and put a HEPA filter in it because the fans, the other components probably weren't designed for that type of airflow restriction. The HEPA filters tend to restrict airflow more than other types of common filters. But in that situation, let's say you want to provide a HEPA filtration system for your home, there are a lot of standalone HEPA systems on the market. They can range from your basic homeowner units that are designed for a small area. You can get those starting at about $200. Then you can go all the way up to medical grade HEPA filters or HEPA air cleaners that can run in the thousands of dollars. There's also electronic filtration systems that can be designed into your ventilation system. These are, you plug them in. They are powered by electricity. And there's a picture of a electronic filtration unit right there. You can purchase allergen filters. Again, these probably aren't going to be effective against infectious microorganisms, but they may help capture some allergens, some common allergens. Now, these are just a few examples. If I was designing an HVAC system or a general ventilation system, and this was my concern, let's say it's a hospital environment, all of these different options are going to be considered. You want HEPA filtration, ideally. Next most effective would be your electronic, then your passive electrostatic, and then your more common air conditioner type filters. But one thing to consider with your filtration systems are the size of the contaminants that you're working with. And that's what's identified here in this chart. And this is a little bit of information telling us, giving us a better idea of the scale or size of these different measurements. 1 micron is 1/1,000,000th of a meter, also referred to as a micrometer or a micrometer. But 1 micron, 1/1,000,000th. 0.3 microns equals 300 nanometers, which equals 300 billionths of a meter. So that's what we're talking about with the HEPA standard. 1 nanometer is 1/1,000,000th of a meter. But let's look at this chart. Let's use the HEPA standard as a reference. Okay, I inserted a red line here to identify the HEPA standard. That's 0.3 microns or 300 billionths of a meter. And many of our viruses are going to be smaller than the HEPA standard. Now, this is the same standard, this 0.3 microns. This is the same standard that's used with respiratory protection devices. A 95% efficient respirator, or an N95, a P95, or an R95, they're only capturing 95% of contaminants 0.3 microns and larger. So there's even 5% of contaminants larger than 0.3 microns that aren't being captured by an N95 filtration or an N95 respirator. Then there's a lot of viruses that are too small to be captured by that level of respiratory protection. And we'll get into this more in our last unit of the semester when we talk about respiratory protection. But that's one thing to keep in mind. It's one of my concerns with everybody wanting to go out and get the N95 or the P95 masks. You're probably not protected from most viruses by that. Here's some other contaminants, combustion gases like carbon monoxide. Some of those combustion gases are less than the 0.3 micron in size. Tobacco smoke, face powder, wood smoke. You're going to be protected pretty well from wood smoke. Bacteria, you're going to be pretty well protected because your bacteria is going to range from a size just above 0.3 microns all the way out to, let's say, 40 microns. Bacteria are larger than viruses. Cooking particles, sneeze droplets, spores, mold. You're going to get good protection with the HEPA standard filter from these other contaminants. Now, if we look down here lower in this chart, it has different filtration devices. Furnace, common furnace filter, passive electrostatic, a pleated filter, electronic filter, and a HEPA filter. Again, your HEPA filter is most effective, followed by your electronic filtration systems. But even then, they're not capturing everything. Again, the HEPA standard is not going to capture a lot of the smaller viruses. Now, I've talked about most of these points already, but I'll just review them with you. HEPA filters will capture 99.97% of particles 0.3 microns and larger. According to the charts down here, this part, HEPA will capture more than 95% of particles to a size of 0.01 microns. But a problem, like I mentioned in the previous slide, they can overly restrict airflow and adversely impact system functioning. So you want to be cautious putting a HEPA filter in a system that's not designed for a HEPA filter. Systems need to be designed ideally for use with HEPA filtration. Electronic filtration designed to work with an HVAC system may be a better option than a HEPA filter, again, for your common HVAC systems. Now, if it's in a medical, laboratory, hospital type environment, then you want to design in the best filtration possible. And pretty much the best filtering standard is the HEPA standard. And I'll say it one more time to beat a dead horse. You're not going to capture a lot of viruses because they're too small to be captured by a HEPA standard filter. Another thing to consider, a common pleated furnace filter may be better than a passive electrostatic filter. All right, I've gone way over. I'm going to hit 40 minutes, and I apologize. I like to keep my modules shorter, but I did want to finish it up with this module. Let's just summarize what we've talked about with regard to general ventilation and indoor air quality. Again, we want to look for indicators of poor air quality as a safety manager. We want to identify triggers that may decrease indoor air quality. If we identify any of those triggers or any indicators, we need to be prepared to investigate further. Investigations would involve interviews, sampling, direct reading instruments, and maybe even bringing in a consultant to help us out. We need to monitor our ventilation systems, proper air volumes, make sure the ventilation's set up properly. In some cases, we need to provide the required air treatment or air filtration systems. In extreme cases, and this will be my final point, if there are widespread health problems in a building, there may be the need to evacuate that building, to abandon that space until the corrective actions can be implemented. Again, that's going to be a rare situation, but that's something to be prepared for as a safety manager. You probably will never encounter a situation like this, but it is a possibility. All right, on that note, I will end this module, which also ends this unit.